Okay, so I got a message about 1.9.26, and I remember looking at it and going, oh, well, you would just have to set them up and then it should fall into place. But then I quickly tried it yesterday and I couldn't get it to work, and then I had to do something else. And then, so I'm feeling like 1.9.26. So on assignment, I want to call it on assignment number 3, I think. Question 1.9.26 will be a bonus question. You can still try it, but it turns out it was harder than I intended. Not good. Okay, let's see here. Oh yeah, I think I said before that we would have test 1 after 2.2. All questions should be bonus questions. I agree. Hey, I'm with you guys. So I think I said we'd have test 1 after 2.2, but 2.1 is kind of, there's a lot of concepts in there. And so what I want to do is I just want to finish 2.1 hopefully today, and then have our test next Thursday. Okay. And so don't jump. Don't jump. It's going to be okay. I've got light at the end of the tunnel. I've made a decision. So what I want to do is I want to finish. So we will finish section 2.1 today. And we'll have test 1, I know, in November. It's because I can't seem to, and I don't want to rush through all this stuff. In my mind, I had a plan for when we would have the test, and then it just was never coming up. So I'm cutting our losses now and saying, okay, we're gonna have our test finally. What's nice about then test 2, of course, we'll have kind of a shorter amount of material. That's good, I guess. So we'll finish section 2.1 today, and test number 1 will be up to and including section 2.1. So I know I said up to 2.2, but no, let's cut it here. This is plenty. And so what I want to do is I want to have a review on Tuesday. So a test 1 review. So Tuesday, we will do test number 1 review. It is usually used in, so integration by parts is really common that we use. I wasn't expecting it so early. That's why I'm like, okay. I think you're right. I think it is integration by parts, but I also think that for that one question, the 1.926, we have to leverage the symmetry. I just haven't had time to like get into it. So that's why it got a little bit harder than I expected. But yeah, integration by parts, we use it all the time. Yeah, it's seeing that pattern, right? Ugh. You get used to, like, there are certain, you just end up having, you know, kind of a toolbox of 10 different functions that you have to deal with. But until then, it gets really it's tricky. So what I want to do on Tuesday, because I promised I would set you guys up for success here, even though this stuff is really, really hard. So on Tuesday, I want to do review. You'll get more than 49 marks. Don't worry. That's all you need, more than 49. No, I know how important grades are. And of course I want you to take some material out of this course, but I know how hard the material is. And I also know how important your grades are for, you know, getting into grad school or whatever you want. So I know that, and I'm not here to bring you down by any means, right? And so I'm going to try to keep your grades up here as long as you're working, and I know you guys are working really hard. So don't worry, it will pay off. It just might not feel like it. So we're going to do a review. And so what I want to do before the review is I'll post a practice test. Now I don't have one made yet, and so it'll be sometime before the weekend. And so I will post a practice test before, I'll say, the weekend for you to try on your own. Okay. And then we're going to go through it together on Tuesday. Now, what I'll do as kind of a bonus assignment is you can submit the work for the practice test just for a completion mark, right? Did you try it or did you not try it? So for a bonus assignment, you can submit your work for the practice test before class on Tuesday. For one completion mark. For one completion mark. That's my favorite kind of marking. Did they do it? Did you try each of the questions? Is there a reasonable attempt? Now, I'm not looking for correct answers or anything like that. Is there some sort of reasonable attempt for each of the questions that I've given you? Yes or no, and then you get a completion mark. And so that should help with the the passing, right? And so let's see here. For one completion mark, you know what? Let's do one better. Let's do okay, so you have to submit it, and I'll put so you can submit on Gradescope. You guys are already pro at Gradescope, so that's awesome. Saw all your submissions there, so that's good. And then so that's how we'll submit the test as well. Now, oh, that's okay. I'm gonna put all your PDFs into one file and I'll upload it. But what's really handy is if you have a scanning app on your phone. So I have an iPhone, so I like Scannable, and it'll just make it a single PDF. So then if you have your work just on a piece of paper like this, then you can just scan pages, 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 and then it'll just make it one document. So because I think that was the problem, but I'll just put it in together in one. That's fine. Because I think that was the problem. Yeah, so you'll want to put it together as one PDF. It's pretty easy to do, at least on. I'm an Apple gal, so I just open one PDF and then I just drop other PDFs in there, and they just get put together. But I can see if I can help you out maybe after. So so you're going to submit on Gradescope. That's going to be the same for the test. And so what you can expect for the test is very similar to the practice test. And I know that's kind of old school, right? But this is old school material. And so I just can't figure out a way to make an online test that's going to be able to test everything that I want. Okay, and so what I'll do for the test will be test number 1, held during class time on November 4th. Okay. And you don't have to have your camera on or anything like that. I feel like this material is hard enough to have to, so you don't have to deal with, oh, I got to set up my camera and everything like that. I think for this material, if you can just sit down and focus on the material for an hour and 20 minutes, that's good. I'm happy with that. And you guys are so advanced that I feel like I should be trusting, and I can be, so that's good. And so I will be here in the Zoom room if you have a question, right, that you think I can reasonably answer. Okay, but so I will be in the Zoom room if you have questions. Maybe I should say a question. You don't have to have multiple questions. So I'll be in the Zoom room if you have a question. Yeah. But you do not need to be here. Okay. That's if you have a question and you want to have me on the line. And I know a lot of people will just kind of log in and have it there in case they need me, but that way we don't have to deal with, internet connections and things like that. So I'll make these kind of bullets here. I'm going to post a PDF of the test at the start of class time. Okay. And so I will post a PDF of the test questions. Well, I mean, I'll post it before, but it'll be available, but doesn't matter. At the start of class. Okay. Just like for the assignments, you write your answers on a piece of paper. Okay. Write your, maybe I'll say, show your work. Show all your work. On paper or a tablet if you prefer, if you have one and you don't mind writing on it. So show all your work on paper and then scan and upload your work by the end of class. to Gradescope. So you don't need to show any graphs, although I think you might find the graphs useful for checking your work. Okay, and so I'm going to finish this point, but then I also want to add that point on here because that's really good. And then scan and upload to Gradescope. You do not need to show any graphs. But you can use Desmos to check your work, right? Oh yeah, those graphs. So you don't need to show them. If you find that it helps support your work, then just do a quick sketch, right? Nothing crazy. So you do not need to show any graphs. Oh yeah, that'll, yeah, if your printer can't handle it, then definitely not. So you don't need to show any graphs, but you are welcome to check your work with Desmos or R. With Desmos or R if you want. Okay. So that leads me to my kind of final thing. It is open book. Okay, so all the assignments that you've worked on, right, you're allowed to access those. I don't want you searching questions online, and I'll make sure that they're not available anyways. Rude, I know, right? But you can use all your tools, right, that are available to you. You can Google things like what is a CDF, what is a PDF, right? I'm not, this stuff is really hard, and we're talking about a lot of different concepts. And so in the real world, we get to look stuff up if we're feeling unsure, right? But in terms of, well, I haven't sat down and made the test yet, so I'm not sure. I'm guessing probably about 10 questions. That's a lot. So, so that's what I mean by, you know, you have to have some knowledge there. Just because it's open book and you can use all your resources doesn't mean it's going to be easy, right? You need to have that kind of core knowledge to be able to move quickly enough through the test. So I'm not going to commit to the number of questions quite yet, because I haven't gone through something that would be reasonable. So I'm guessing around 10. You may use all your resources except each other. Except each other. And other, you know, let's call them cheating mechanisms. I think that used properly, places like Chegg and stuff like that can be really useful, right? But in terms of tests, we all know that that's inappropriate. And so, of course, that's off limits. But in terms of, you know, using, finding a summation calculator, as long as you're able to show where you got stuff from, that's fine by me, right? Because there's a lot of stuff here that that we probably don't know off the top of our heads. Okay, so you may use all your resources except each other, and I'll say cheating sites such as Chegg. Okay. So you have to work alone, of course, and you can't just put it on Chegg and get someone else to do it. Hard to do on a time crunch too. I haven't used it. I'm not too familiar, but I know it's, you know, a lot of people are really hung up on it being available. And but I will say this, before the test, I will go through and make sure that none of the questions that I'm asking are coming up on Chegg and other places. So if they end up coming up after the test, then that's really bad, right? And we would have to deal with that. But that's my warning, I guess. Don't do it. All right. So any other questions about the test? So it's going to cover all the material that we've looked at up to and including today. So if we don't have any, I haven't seen any questions come in. So maybe I'll just keep going in section 2.1, which honestly, it feels like forever ago that we did. I think I'm going to have time to finish all this stuff, but I'm kind of leaving it open. If I don't have time to complete 2.1 today, then what I'll do is I'll post a video and we'll use that for the lab tomorrow. Otherwise, we're just going to keep chugging through those basic R videos because that's nice, easy marks if you've done them before. And if you haven't done them before, then hopefully that they're useful just for building up our skills. Okay. I'll end that there. So we'll see what happens for tomorrow. Either way, it's going to be a video because no one wants to come to class on a Friday. All right. Section 2.1 continued, because I haven't seen any questions. So chapter 2 is when we introduced two random variables, right? We've got an X and a Y, or maybe an X1, X2. So now we have two random variables and maybe they're acting together, right? And so then we introduce this idea of having a joint PDF, right? Or a joint PMF. Okay? And so what we can do is, even if we have a joint PMF or a joint PDF, PMF is for recall, a PMF is for a discrete function. Or maybe a discrete random variable, let's say. Whereas, and this doesn't look like an M. Whereas a PDF is for a continuous random variable. Let's see if I can recap what we did so far with two random variables. With two random variables, we have a joint PMF or a joint PDF. Okay. We can have a joint PMF or PDF. Let's see here. I didn't write down a quick summary, but for the PMF, so for the discrete case, we have the sum. Let's see if I want to the probability, we'll use square brackets here, that x, y, so some combination of x and y, where x and y are random variables. Clarify that there. So the probability that xy is in some space A is the sum over all the x's and y's that are in A, so that apply to A, over the joint PMF. Sorry, I didn't have anything, a quick summary here. So the PDF, if we have a continuous function, then the PDF is going to be, where's a good summary? The probability of x and y in some space A, now we're going to be doing a double integral over xy in A. Oops. Bracket doesn't go there, it goes here. Because it's a combination of x and y. I'll clean that up. fxy, xy, dx, dy. Okay. And maybe instead of using these shorthands, because they're not very telling, I'll say discrete and continuous. That's what it was meant to mean, but I just want to be explicit. Okay. So what we have here are the joint PMF or the joint PDF. Notice how my pen keeps kind of clunking out here. I don't know why it's doing that. It's been doing that for a little bit, but who knows? So this is the joint PMF, and this is the joint PDF. All right, we can develop these probability density functions or probability mass functions with a combination of x, y random variables. So now what we want to focus on is we're going to introduce this concept of marginalization. So if I have, for example, a joint PDF, then I can reduce this to be just about X or just about Y. How can I do that? What's your kind of main guess? Well, you can integrate over whatever variable you don't want, right? Or that you don't care about, right? You consider all the possible options for Y, for example, and then you have your PDF for X. It's going to be a little bit more, but that's how it works for the summation, at least. Okay. So what we want to introduce is called marginalization. So if we're only interested in some probability that X equals some value, right, and we want to consider all possible values of Y, then one of the events we can define given the probability distribution for two random variables, given the probability distribution for, oops, that's the wrong two. Weird. For two random variables, X and Y, is X equal to X for some value X? So if we have two discrete variables, okay, then what we can do is we can look at the sum over Y, for example, if we're interested in X. In the case of a pair of discrete, I'll highlight that because that's going to be the difference between these two comments that I'm making here. So in the case of a pair of discrete random variables, the probability that X equals X is going to be the sum over the Y's. And I've got this page break here. So what I'm going to do is I'm going to bump it up just so I have a little bit more space here. So it's going to be the sum over all the possible Y's of this PMF, PX. Right, so sum over all possible Y's. Right, and then that's going to get you back to just the PDF or the PMF for X. Yeah. So here, this pen is cutting out again. Weird. We recognize this, the probability that X equals X, as the PMF, right? So we recognize the probability that X equal to X as the PMF of X. Okay. And we call it, because it came from a marginal distribution, we call it the marginal PMF. I said the marginal distribution, but I meant the joint distribution. So we recognize as the PMF of X, but because it came from a joint PMF, that's what I wanted to say. We call it the marginal PMF Px of X. And we can define both scenarios. So for X1, X2, or X and Y, it doesn't matter. But we have Px of X is the probability that X equals some X. So this is the same one that we had up above. And that on its own is going to be the sum over Y, Pxy of Xy. And then Py of Y is going to be the probability that Y equals Y. We do the same thing, we just sum over the X's on the joint PMF, joint distribution function. So we had a coin flip example where we introduced this idea of having a joint PMF for a discrete case. And so we're going to return to that. And we can generate these marginal PDF or PMFs, right? By looking at it like a table. And you've actually seen these marginal probabilities, the joint probabilities, you've seen those when you did probability in Stat 230, but here they are more rigorous. Okay. So returning to our coin flip example, we can write the marginal PMFs for X and Y in the margins of the tables. So conditional probabilities require the joint probabilities, but the conditional probability is the joint probability divided by the marginal probability of the given event. Because, right, just I'll erase this, but just to illustrate, the probability of A given B is the probability of A and B divided by the probability of B. This is just in general, right? And so this is the joint probability, and this would be the marginal probability. But I'll erase that. We can write the marginal PMFs for X and Y in the margins of the table. Hence the name. Yeah, so the joint is the intersection, the probability of both happening at the same time. So we've got PXY of XY in general, and I think I need 0, 1, 2, 3. I think it was the number of heads and then the number of flips until the first head or something like that. It doesn't really matter because we're just going to be looking at this table just for the probabilities. So if X can take on 0, 1, 2, 3, and Y can take on 0, 1, 2, 3, then I'm just going to jot down these from left to right across the rows here. It's going to be 0, 0, 0, 1 over 8. Then going down to 1, 0. It's 1 over 8, 1 over 8, 1 over 8, 0. Next line, 2 over 8. Because we might not remember, but we saw that two outcomes were identical to each other, even though they came about in a different. If it comes back. Okay, looks like I'm back on my end. Yeah, no doubt. It says my internet connection is unstable. That is so weird. Were you guys experiencing some? I'm gonna see if I have something running. I don't think I do. Okay. I didn't really have anything running. Hopefully we're back on track. Okay. I'm not sure what to do, but we saw that the situation where X was 2 and Y was 0 came about in 2 different ways. And so the probability of that then was 2/8. And then we move on, 1/8, 0, 0. And then 1/8, 0, 0, 0. Okay. So here, what you do when you do these totals, here, you're looking at all the possible values where X equals 0 over all of the Y's, right? And so each of these rows is going to be where X equals 1, where X equals 2, where X equals 3, right? So together they make up the marginal PMF of X. So we've got Px of X, and all we have to do here is sum across each of the rows, right? And so it's going to be 1/8, 3/8. Keep it as fractions, otherwise it gets really weird. 3/8 and 1/8. Whereas now, if we sum down the 0 column, for example, that's the probability that Y equals 0, regardless of what the X is, right? And so now the column here, the row, the bottom row, is the marginal PMF of Y. So we can denote that by PY of Y. And we sum down the column. I get 4/8, which you could simplify, but I'm going to leave it as over 8 in case I have to do any other math. It's just nice to have a common denominator already. And so I'm going to leave it 2/8, 1/8, 1/8. And of course, regardless of how you got there, whether it be through the columns or through the rows, you're going to get a total of 1. Okay. Okay, so that's how it works for a discrete function, and so, or for two discrete random variables. So now let's have a look at the continuous case. So for a pair of continuous, and I can't remember how I highlighted it here. I'll highlight. An actual highlight is what I used. So for a pair of continuous random variables, remember, for a continuous random variable, the probability that X equals some value is always 0, right? Because we need some interval to find the area under the curve, which is the probability, right? And so we can't do that if there's no area, right? If the width is 0. So we know that the probability that X equals X is 0. But what we can do is kind of in a roundabout way is we can find the marginal CDF, right? The cumulative distribution function. So all the probabilities up to and including that point. And then we can take the derivative of that marginal CDF to get to just the marginal PDF. Oh, marginal, marginal, marginal. So, but we can find the marginal CDF. Which is going to be fx of x, which is, remember, the probability that x is less than or including some x, which is going to be the integral from -infinity up to some x, right? Because you want to go up to x, but not before you integrate over all possible values of the y, right? You need to get rid of the y's before you can generate the probability of going up to x. Okay, so the x less than or equal to x, that's taken care of at the very end. Okay, but what we have to do here is we have to take the integral over y. Now, y is allowed to go from negative infinity to infinity because we want to consider all the possible values of y again. fxy of, I'm calling it ty because x is already taken here, right? So x, because I want to have the probability that x is going up to and including x, I want to have x here, but I don't want to use the same x variable here because it's going to get too messy. And so ty and maybe that arrow should go the other way. Since x is in the integral, it would be too confusing here as well. So we can replace it. We can call it t or whatever you want. There are a lot of values or a lot of letters that are already kind of taken, right? You could call it a if you want to, that's allowed. B, C is used for a constant, right? F, you can't use F, that would be weird. It's a function, right? So T is fine. And I want to take the derivative with respect to y, right? And so I need to have the dy on the inside. It's an inside job here. And then dt. So this is integrate over all y's first, and then integrate with respect to what used to be x, but now we're calling it t just for simplicity's sake, up to the value x. Okay. But that's just the CDF, right? How can we rework the CDF to get to the PDF? Well, we can take the derivative. That seems weird, right? But that's one way of doing it, right? And it's the most common way. So, and then we take the derivative of fx of x, okay, to get the marginal PDF. To get the marginal PDF of x. So fx of x is f prime x of x which is okay, which is, sorry, I just want to write it down here, the integral from negative infinity to infinity of fxy, so that joint PDF xy dy. Right, because what would happen? So here you've basically got the same thing, because if you integrate it and then you take the derivative, well, you're just back to here, right? And likewise, Fy of y is also going to be the integral from negative infinity to infinity of that joint PDF over x and y. Integrate out the x. So notice how we got here in kind of a weird explanation kind of way, but that is what we're doing. But then what ends up happening is we really just integrate over all possible values of y, right, to end up with the marginal PDF of x. So what we said was what we're doing is called marginalization or marginalizing. And basically how I think about it is we're summing or integrating over the variable that we don't care about, right? The one that we want to kind of get out of the way, right? Oh yeah, let's consider all the possible options there. And then we don't have to deal with that anymore. So the act of summing or integrating over arguments we don't care about. I'll put it in quotes. We do, but temporarily we might not. We don't care about like intersection with the union. Yeah, kind of. That's a fun take, but yeah, kind of. Because you want to look at the joint and then similar. Okay, fun. So if we sum or we integrate over arguments we don't care about in order to get a marginal probability distribution or get a marginal probability distribution, is called marginalizing. Okay. So, good. I'll underline it there, then it's all together. We can also talk about expectations, right? So expectation values, or I call them expected values sometimes because to me it sounds better, but they are expectations. And so they're, we saw them in the single variable case, right? The expected value of x. Now we have x and y, so we can still find expected values, except we have to consider both x and y. Luckily, the expected value remains linear, right? So what that means is we can just plunk it onto the random variables. So the expectation just latches onto the random variables. And I'll show you what I mean. But first, I jumped ahead. We need to define the expectation. So expectations. We can define the expectation value the expectation value of a function of two discrete random variables as the expected value of, we'll call it G, mix things up. You could use F here if you wanted to, but G of x1, x2 is just some joint PMF because we're going to let it be discrete here. And so it's going to be the sum over x1, x2, so all possible values of x1 and x2 of that function, g of x1, x2 times the probability function of x1, x2. Before, right, in the single random variable case, what did we have? We had the expected value of g of x was the sum, and then it was implied that it was over all the x's of over x of g of x times p of x. So you can see how we just do the same thing, but now we have two variables. So we need to have the joint PMF of x1 and x2, and then we've got some function defined in terms of x1 and x2. A function in terms of x1 and x2. And then here, this is the joint PMF of x1 and x2. All right. Same thing, it just gets complicated because now we have two variables. Okay. So that was for two discrete random variables. And for two continuous random variables, highlight the differences here. Should be obvious. As soon as you have a continuous random variable, that's when you're going to have an integral, whereas a summation is going to come from a discrete random variable. So, and for continuous random variables, as the expected value of g of x1, x2, so some function of x1 and x2 is going to be the sum from, or sorry, the integral, I should say, negative infinity to infinity, negative infinity to infinity, g of x1, x2, and maybe should try to make these lowercase because now we're working with them. x1, x2 times the joint PDF f of x1, x2, dx1, dx2. So I'll match this here. A function in terms of x1 and x2. And same thing here. This will be the joint PDF of x1 and x2. Right, same thing as before. We're only going to consider, oh, my little baseball cap slipped down here. it's not, it's a piece of paper. But in each case, right, we only consider the valid values of X and Y. And we also assume that the expectation only exists if it doesn't go to, so if the sum doesn't spiral off to infinity, or if the integral doesn't spiral off to infinity, then we say that it exists. So in each case, we only consider the expectation value to be defined if the relevant sum or integral converges absolutely. That is, if the expected value of the absolute value of g of x1, x2, and absolute value is less than infinity. Right, so if it goes to some value, essentially, then we say that it's defined. That's going to be the case, right? It's just, if you're doing questions that I haven't assigned out in the real world, I doubt it, but then that's something you have to keep in mind. But for us, they always will work. So the expectation is still linear, right? Because the summation is linear and the integration is linear. And so note that the expectation is still linear, meaning the expectation of some k1 g1 of x1, and maybe that's x1 x2 plus k2 g2 over x1 x2. Why do we have so many? So we're allowing a constant in front of some function of x1, x2, and then we might be adding a constant times some function, a different function in terms of x1 and x2. So that's still going to work. But what happens when you want to bring in this expectation, then it latches on to the functions of x1 and x2. Yeah. And so what happens is we have k1 gets bumped to the outside, and we can multiply it by the expected value of g x1 x2 plus k2 times the expected value of g2, that should be g1 x1 x2. Yeah. So it's linear because the expectation just latches on to, we can distribute E onto functions of the random variables, onto functions of the random variables. All right. Okay. So, doing great. So these are all just kind of saying, okay, well, everything that we learned, it stays the same. It's just we're going to have more complicated values, right? And so to find the expected value over a function of two variables, then we need to integrate twice, right? We need to do this double integration But then the idea stays the same. We have some function of x and y times the joint PDF, and then we integrate with respect to x1 and then x2 strategically, right? There might be one that's easier than the other to do first, right? But the idea stays the same. Same thing with the moment generating function. So the moment generating function is the expected value of e to the tx in the single variable case. So now we're going to have a multi or a bivariate case. So because we're only considering 2 variables right now, we could extend it to many more variables, but we don't want to do that. 2 variables is plenty. And so we can talk about the moment generating function, and that's what I want to do here. The moment generating function. So recall for a single random variable, we said that m of t, the moment generating function, MGF, m of t is the expected value of e to the tx. And maybe I'll say a single random variable x. Okay. And then what we said was, okay, sometimes it's going to be easier to work with the moment generating function. And so the expected value of x to the power of m, let's say, is going to be the mth derivative of the moment generating function evaluated at 0. Okay. And so we found that the expected value of x to the, I'll say m, is the mth, and maybe I should do, I won't use brackets there, the mth derivative of m evaluated at 0. Okay. The mth derivative of the MGF evaluated at 0 at t equals 0. Okay. Let me just find that. Maybe I can send you to the right section. I feel like it was 1.9. Yeah, I feel like it was 1.9. Okay, so it's the mth derivative of the MGF evaluated at t equals 0. Now that's maybe easier, maybe not, right? So if you want the expected value of x to the power of 3, right, you can do that if you have a nice PDF, or if the moment generating function is easier and you like taking derivatives more, then you can do that. Okay, and so now, in the case of a pair of random variables, oh, my pen's doing that thing again. We can define the MGF as m of t1, t2. So now it's a little bit tricky because the moment generating function is in terms of t1 as well as t2. So now we're going to have a vector, but it's going to be the expectation of, oh, pen is not cooperating here, e to the power of t1 x1 plus t2 x2. Oops. That's the same idea, right? E to the power of t times x, but now I have t1 and x1 and t2 and x2, right? And so now I have to take all those into account. So this is the same. I can write this out, and sometimes this is a little bit nicer to look at, but I can write this out in terms of vectors. And so it's the expected value. Oops. Come on. It's so stupid. It's like my Apple Pencil is running out of ink. I don't know how else to describe it. The exponential, so e to the power of, and then I have t1, t2, the transpose. So this here is the transpose of the vector times x1, x2, which is also a vector. Okay. These two are saying the same thing, right? So if I have the transpose of this vector, then I have it laying flat like this, t1, t2, and then I have x1, x2. So I can multiply those and I would get t1, x1 plus t2, x2. This is the same, and we can write it as the expectation of e to the t, and that's a vector, so I'm going to put a little half an arrow on top, transpose x vector. And I'll clarify here, where t, the vector t transpose is the transpose of the column vector t. So we can get the MGF for each of the random variables, so x1 or x2, kind of similar to how we found the marginal PMFs or PDFs. Okay, so we can use the joint MGF. We can get the MGF for each of the random variables. Guess I could have abbreviated there. It's okay. From the joint MGF. So I've got mx1 of t1. Okay, so now I'm only concerned with x1 and how it corresponds to t1. And so that's going to be my joint MGF, mx1, x2 at t1, x is 0, or t2 is 0. So that's nice. And mx2 at t2 is the margin, or the joint MGF, mx1, x2 at 0, t2. So whichever one you don't want in there anymore, you just look at T2 equals 0 or T1 equals 0, depending on which one you want to get rid of. So we can use it to generate moments just like we did before, but usually we just end up using the MGF as a way to identify distributions, okay? But we can do it. What would we have to do? We would have to, just like we said here, we could take the mth derivative and evaluate it at 0. But now I have multiple random variables, x1 and x2 instead of just an x. Okay, so now I'm going to be able to use this MGF to find those expected values. But we usually use the MGF as a way to identify distribution or to identify the distribution. But it can also be used to generate moments, as in the single variable case. Which is going to look like the expectation of x1 to the power of, let's call it m1, x2, m2. Okay. Is going to be the derivative, so of the mth one plus m2 ith derivative, del m1 t1 del m2 t2 of that moment generating function mt1 t2 evaluated at t1 t2 equals 0 0. Okay, just under the wire. The clock just turned. So test 1 is going to cover up to this point. And what we'll do for tomorrow is I'll do the same thing. I'll post one of the lab videos for you to work through, and then that'll kind of let you work through some R code. But hopefully it's a little bit better. I'm around if you have questions while you're working, if you're working through the lab during the lab time, but you can just watch it on your own time. So I will make a note here that test number 1 covers up to here. Okay. If you have any questions, let me know. Otherwise, you'll hear from me before the weekend because I'll let you know when I've posted the practice test. But otherwise, I'll see you on Tuesday. Okay, stop this recording here.